So I'll be the presenter today, and I'll be talking about the topic on final data assessment of air pollution and respiratory diseases in South Korea. Air pollution, accompanied by economic development, is expected to exacerbate with further development, and this leaves air pollution a severe global problem. Air pollution leads to early deaths and productivity loss due to lung and heart disease. Air pollution contributed to over 4.2 million deaths and 103 million lost years of healthy life worldwide in 2015, of which 59% were developing in Asia. So many countries are seeking ways to decrease air pollution, especially particulate matter, which is a major air pollutant. In Germany and France, the use of all diesel cars in major cities is regulated, and London is considering car-free days throughout the year. South Korea is one of the fastest growing economies among OECD countries. However, such economic growth has come with air pollution. South Korea has the worst air pollution among OECD countries. In a joint study of NASA and South Korea, they found the foreign contribution to be 48% and the remaining as domestic costs. Domestic causes include industrial facilities, power plants, and diesel vehicle emissions. And foreign causes include yellow dust blown by westerly wind from China, which is a heavily coal-consuming country. This is a global map showing annual particulate matter measured from NASA satellite in 2015. The enlarged part shows the map of China and South Korea. As you can see, the eastern part of China and the west part of South Korea is heavily polluted. And this kind of touches on the subject that the wind blown from China might affect the air pollution in South Korea. Air pollution affects the economy through productivity loss and respiratory health. This paper focuses on the health impact of air pollution. Since air pollutants easily travel through air affecting neighboring districts, the districts are spatially dependent regarding air pollution and respiratory diseases. This study employs panel analysis to investigate the impacts of air pollution and its spatial dependent effect on public health. I included 120 districts of South Korea over 2010 to 2015. The first result is a panel analysis with controls for environmental, economic, and demographic factors of each district. And the second part is panel analysis with spatial dependence of pneumonia patient rate, which is a dependent variable, and particulate matter, which is the explanatory variable. And the last part is the robustness check with robust standard error and logistic transformation of the dependent variable. Previous studies include Medina Ramon, who found stronger effect on particulate matter during warm seasons in 36 US cities, and Hui, who identified the effect of particulate matter on most susceptible subpopulations in Hong Kong, and Son considered different effects on pneumonia according to different age groups in 8 cities of South Korea. The main methodology used in this study is the panel data regression. The Y is a dependent variable of each district at year T. And the main explanatory variable is particulate matter, which is denoted as PM10 in this equation. And X includes all other explanatory variables, and UI is the unobserved individual effect, and the last term is the error term. And the second analysis is the panel data regression with spatial dependence, which we use the method from Lee and Yu. The equation is basically the same as the panel data regression, but it includes the weighing matrix and the dependent variable term, and the weighing matrix and the particulate matter explanatory term. W is the spatial weighing matrix, which is a 120 by 120 matrix, and it is composed of the relationship of all the districts that is included in this study. This is a map of districts within Seoul. The center part or district is numbered as 1, and it is correlated with surrounding other districts. So the weight component of 1, 2, 3, 4 is given a value of 1. These are the variables that I used for the study. The dependent variable is the number of pneumonia patients divided by total population, which we denoted as rate per 1,000. And the main explanatory variable is PM10, which is number of days which daily average of PM particulate matter exceeded 150 micrometer per kilometers. And other factors were also considered as well. This is the summary statistics. The important part here is that the PM10 mean is about 2 and the maximum is about 14 days. And the standard deviation is approximately 2 days. This indicates that there is a large variation in the number of high PM days and that extreme events of particulate matter was apparent in South Korea. This shows the graph of rate of pneumonia patients, rate per 1,000, and the number of high PM days. As you can see, the overall trend of both these variables are quite similar. It first increases and then decreases, and it is currently increasing. This is the main result of the panel data regression. The statistically significant variables include PM10 and old and young. Old is the variable indicating the population of 65 years or older, and young is the population of 10 years old or younger. The coefficient of PM10 indicates that it is positive, which can be interpreted as the increase in number of PM days is associated with an increase in the rate of pneumonia patients. And the coefficient for old and young was also positive, which indicates that the old population and the young population are especially susceptible to respiratory diseases because they have a weak immune system. And the smoking rate of each district was positively related to the rate of pneumonia patients. This shows the panel data regression with spatial dependence. The first model includes a dependent variable, or the rate of pneumonia patients, as having a spatial effect. After conducting the spatial effect, it can be seen that the PM10 variable is still statistically significant and positive. And also the weighing matrix of the pneumonia rate was also significant. The second model includes the number of high PM days as the variable as having a spatial effect, and it also shows that the PM10 variable has a spatial effect and it is statistically significant. And in the last column, you can see that the PM10 and the dependent variable is included as having a spatial effect, and it shows that the PM10 is statistically significant in this occasion as well. So this indicates that the rate of pneumonia patients and the number of days with high PM is spatially dependent. So the pneumonia patient and PM10 in one district is likely to be associated with high PM10, high pneumonia patients in other districts. And the overall the data is explained well by this model, as we can see by the wall test, which the probability is less than 1. This is the robustness check of the panel data regression with the robust standard errors. The one thing to point here is that the coefficient of PM10 is positive and statistically significant, which is in line with the first panel data regression result. And this is the estimate result with logistic transform dependent variable. Although the coefficient is very small due to the transformation of the dependent variable, the important thing to note here is that the PM10 variable is still statistically significant. Air pollution is a severe global issue, and particulate matter is high in South Korea, which has increased to the level of deteriorating respiratory health. This study investigates panel analysis with fixed effect, and it also includes panel regression accounting for spatial dependence of districts. The study finds statistically significant association between number of days with high particulate matter and pneumonia patients. Considering the spatial dependence of districts, the fixed effect regression also used positive and statistically significant association between number of high days of PM and rate of pneumonia patients. This study only investigates the impact on pneumonia patients, and other respiratory diseases such as asthma, lung cancer, or COPD, and the economic activities will be added to study the impact of air pollution. As for the model with spatial dependence, the weighing matrix needs to consider the wind direction to account for the effect of westerly wind that is prevalent in Korean Peninsula and affects the air pollution in Korea. Thank you.
This is my first visit to Korea, and the level of air pollution that you have mentioned here regarding the PM10. Have you measured PM 2.5?
I only included PM10 for this study.
PM10.
Yes.
What is the distribution and spatial distribution pattern? Because in Korea that I have seen, there the land mass is undulating. So from the lower level to upper level, is the distribution of the PM10 is uniform or it is different? Because the spatial distribution related to the temporal variation may be affecting the respiratory disease if it is PM10 or not.
About the distribution?
Yes, PM10 level.
Yes. The distribution of PM10 level of each district is not very uniform because in some districts there are industrial facilities that is concentrated. So in those districts the PM10 level will be high, and in metropolitan areas as well.
What are the sources of your PM10? Because industrial sources itself, the Korean itself. I'm not talking about the China, that is the coal producing area from where the wind is coming and affecting this itself. Korea itself, what are the sources of this PM10?
The main sources include industrial facilities and
Industries.
yes, and
The type of industries is?
Pardon?
The type of industries?
A manufacturing sector.
Factories.
Yes, and also car emissions are major sources of particulate matter too.
Car emissions.
Yes, these are car emissions.